So let us now look at a simple linear regression problem and review some of the key concepts in machine learning. So imagine we have a data set in the form these scattered points. So this is the x-axis, this is y-axis, and so we have x and y, so x1, y1, x2, y2, and let's say we have n measurements. And let's say we try to fit a line to these measurements, the simple regression problem. By assuming the model is in the form of a line, we are assuming the regression model is in this form, theta1 plus theta2x. And the goal of the regression problem is to find an optimal set of values for theta1 and theta2. But in what sense optimal? So if you look at this, the data points, basically from any two pair of data points, we can find unique values for theta1 and theta2 because we know from any two distinct any two distinct points can pass a unique line. But obviously, we cannot just go and randomly pick those 2 points because then theta1 and theta2 would be optimal for those 2 points, but it would be probably a bad choice for the other point. So it is clear that the choice of theta1 and theta2 should respect all points, and we have to formulate a problem so that we can find an optimal theta1 and theta2 so that this line is a good representative of all data points, not only 2 data points. So basically now we have more equations than unknowns. So this is really an overdetermined problem. And so the question is that how can we find, mathematically formulate a problem to find the best theta1 and theta2? So one way to do that, this is probably the most common way of doing that, is by forming a loss function and a particular loss function. So so we want to find theta1 and theta2 such that a measure of error is minimized. Okay, so this would be the prediction of our model. So if I plug in any particular xi here, theta1 plus theta2 xi, so if I just evaluate this model at xi, this model gives me a prediction for xi. We also have the measurement value for that point, which would be yi. So if this is the prediction of the model, we also have measurements. Which is given by yi. And so the difference between what the model predicts and what we have the measurement, it's a good measure, is one way to measure error, just the distance between these two predictions. So if we subtract the prediction of the model, if you evaluate the model at xi for a set of parameters theta1 and theta2, and maybe I can just write that explicitly, theta1 and theta2, and then subtract the prediction of the model. So this would be the error at point xi. Right? So the value is yi, and the value that the model predicts is f of xi at these choices of theta. And so obviously this would be just the ith point. So we want to look at all points. So you need to sum up the error. But if you just sum up the error in this form, so let's look at this value here. So this value, for example, for this point would be this distance. And yi, here yi is smaller than the prediction of the model. For this point, this value would be a positive number. But if I look at this point, yi, which is the value here, is larger than fxi, so this would be a negative number. So these two areas, if I sum them up, they will cancel each other out. So one way is just to put absolute values, and another way is to take this to the power of 2 and then sum them up. The reason we take this to the power of 2 is that now this is any number to the power of 2 is a positive number. So we are really we don't distinguish between positive or negative error, and we sum them up, and so we don't allow cancellation of positive and negative errors. Okay, so, and I can put 1 over n here to normalize this to a nice number. And so if you look at this quantity, this E, this E is a function of theta 1 and theta 2 for a given data set. And it measures the overall, or it basically sums up all these lines to the power of 2 and then averages them. So one can reasonably conclude that if we minimize this function versus theta 1 and theta 2, so if we find a theta 1 and theta 2 such that this scalar quantity is minimized, then that should be a good quantity. And so basically, so in the machine learning terminology, let me also introduce that, then I'll write down the optimization problem. This very function is called the loss function. So this is the loss function. Right. And this particular choice of loss function is called squared loss function. And let me just emphasize here, this is not the only way to formulate the loss function. In fact, you can come up with your own loss function, and that can have profound impacts on the type of model that we are training. So this is just really the simplest choice of formulating a loss function. So we can plug this particular expression for f here, and basically our optimal theta 1 and theta 2 are theta 1 and theta 2 such that this function is minimized. And so I have theta 1 plus theta 2x I minus yi. Okay, in the next video, we'll see how we can actually solve this optimization problem. This is now an optimization problem. So find theta 1 and theta 2 such that this loss function is minimized. If you look at this loss function, this is what we call a convex loss function. So what does that mean? That means if you plot this, let's plot that in a one-dimensional setting. Let's say I only had one variable. So this is a function that if you plot it, and we can discuss that in future lectures, why this is a convex function. So this is a function that only has one minimum. So as opposed to a function that would look like that. Okay? So this is which has more than one minima. So that would be a non-convex function. But this is a convex function. And so basically, it's like a bowl. And we know it's a smooth function. So whenever it's minimum, the slope of this function is equal to 0. So here, del E del theta 1 at the minimum at this point is equal to 0. Because the slope is negative here and then 0 and positive here. So it has to become 0 at the optimal point. So here I'm using partial derivative to be consistent with this notation, but this only has one variable. So if you really find a point where this number, this E, becomes minimum, extension of this to 2 dimensions is that to take the derivative of this E with respect to theta 1 and set it equal to 0, take the derivative of E with respect to theta 2 and set that equal to 0. And then we should solve that system of equation to see what optimal values we find for theta 1 and theta 2. And that's what we will do in the next lecture.